All this time, we've kind of been glossing over batteries, just pushing it off to a later date. But we've reached a tipping point now where the next video might not make complete sense if we don't have a good understanding of how exactly a battery works. This video will involve some chemistry, and not a lot of physics, because batteries are essentially a marvel of chemistry. But we'll try to be really detailed with our explanations here and go slower than usual. Another goal we have is to come away from this video and really understand why batteries are fundamentally different from capacitors. It's very common for students to get the two mixed up in thought process because in our circuit diagrams we display them as both having a positive side and a negative side separate from each other. Supposedly, both also store opposite charge on each side. So how exactly are they different? They seem about the same to me when we frame them that way. The first major difference is an operating difference, or a functional difference. While capacitors operate by maintaining the same capacitance across the conductors, a battery operates by attempting to maintain the same voltage, or the same potential difference across its terminals. The second major difference is how they behave with respect to charge. We know a capacitor is simply a pair of conductors separated by an insulator, and capacitors act to store a charge difference between the conductors, with positive Q on one conductor and negative Q on the other. This is actually the purpose of a capacitor. The purpose is merely to store excess charge differences and electrical energy between the conductors in the form of the electric field. If that's the purpose of a capacitor, then why have capacitors at all if a battery stores a charge difference too between its terminals? Batteries power all our mobile devices today anyway, so who needs capacitors? Why not just use batteries for all our charge storing needs? The answer is that batteries don't actually store a charge difference. To see why, let's think back to a capacitor. Imagine we connect a charged capacitor across a resistor. What would happen? Well, now that the two plates are connected, the entire system becomes a single conductor, and it's going to allow charge to move through it until it's at a constant potential throughout. It's easy to think that the charge movement happens like this in a steady fashion. In fact, we might have even animated it kind of like that previously, but that's not actually how it works. Instead, the flow of charge looks something like this. Whoa! Let's slow that down so we can see it more clearly. The current through the circuit seems to be correlated with how much charge is left on the capacitor, and it looks like we get a large burst of charge in the beginning with rapidly diminishing charge flow near the end. We'll see how to quantify all this in a later lesson, but for now at least we can say that capacitors are good for short bursts of high charge flow and bad for persistent steady charge flow or electric current. And then in practice, batteries, it turns out, are good and bad for the opposite. Then if batteries don't actually store any charge difference between their plates, where is all the charge? Why is it that when we connect a resistor across the terminals, we get a steady current through that resistor? What's actually going on there? The reason is that while capacitors store energy in the form of electrical energy via the electric field between the conductors, batteries store energy a little differently. Actually, it's unclear whether or not it even makes sense to say batteries store energy at all, but we'll just say for now that batteries store energy in the form of chemical energy. The thing is though, a battery is much more complicated than a capacitor. A capacitor only has a couple fundamental moving parts, but every battery has multiple moving parts, so we must understand why each and every part is crucial to the battery's operation. Also, we're just going to try and understand a specific type of battery introduced in Intro to Chemistry classes, but we should note that modern batteries can be a bit more complicated, and not every battery is exactly like the one we're about to demonstrate. Imagine we have two electrically neutral pieces of copper, and we just touch them together. That's it. What would happen? In this case, nothing actually happens, which is maybe not surprising or all that exciting. So now let's think about something else. What if we have one electrically neutral piece of solid zinc and an electrically neutral piece of solid copper, and we touch them together? What would happen then? Still probably nothing. Assuming anything does happen, it would be at such a small scale that it would be almost impossible to detect without highly advanced equipment. Okay. Let's branch off to a different idea and focus just on the zinc for a second. What if we take this zinc and we stick it in an aqueous solution of zinc sulfate? Seems kind of random, but just go along with me for a second. The aqueous solution is composed entirely of doubly positive zinc 2 plus ions and doubly negative sulfate 2 minus ions. Doubly positive just means for every zinc ion, it would take 2 electrons to make it neutral again. And the doubly negative on the sulfate is just the exact opposite charge. Now what would happen? Again, nothing. The ions are just bubbling around unpredictably with no reaction actually taking place. Okay then. Moving over to the piece of copper, what if we stick it in an aqueous solution of copper sulfate? Here we have copper 2 plus ions and sulfate 2 minus ions. So what would happen here? Again, nothing. It seems like no matter what we try, nothing exciting seems to happen. This is the nature of scientific discovery. All of the great scientists from centuries ago whom we cherish today, this was essentially what their life felt like on a day-to-day basis. They tried doing so many different things, and almost all of them would lead to nothing useful or exciting. But every once in a blue moon, they'd stumble upon something special, and that something special would be enough to change the world. That something is all we remember them by. We don't see the painstaking trial and error that eventually brought them toward that something, even if the trial and error was more than 99% of their effort. So now, what if we take these two beakers, one with a solid piece of zinc in aqueous zinc sulfate, and the other with a solid piece of copper in aqueous copper sulfate, and we connect the two pieces of metal together via conducting wire? Wow, fascinating. Electrons flow from the piece of zinc to the piece of copper. Wait, what? Why? Nothing happened when we just touched the piece of zinc to the piece of copper, but now you expect me to believe that them sitting in these magic tubs of liquid all of a sudden turn them into an electricity generating machine? Well, yeah, I mean, that is what's happening, and it's not a one-off thing either. This is a repeatable experiment we can do. So we have to try to understand the mechanism at work here. Now let's consider everything we know up to this point. Zinc and copper are two highly conductive materials, and now we've connected them with conducting wire. So what do we know about connecting two conductors, either by touching them together or connecting them with conducting wire? The two conducting pieces of metal now allow charge to move until the entire conductor combination is at the same electric potential everywhere. But there has to be something else going on here, because we started out with electrically neutral pieces of metal, so if they're neutral, they have to be at the same electric potential. So what's really going on here? This is where we fall into a pickle with respect to physics alone, and we now have to start introducing chemistry into the mix to make progress. There is actually another form of potential that we haven't discussed up to this point, and it's called chemical potential. Fundamentally, chemical potential is a thermodynamic quantity, and the mathematics behind it can get really complicated real fast. But at a basic level, chemical potential can define a difference in potential between two different species or two different materials. With that, it's useful to define a new quantity called the electrochemical potential, and it's given by this equation here for any species we're dealing with. Now, I don't expect you to actually end up making use of this equation at the intro level, but there's a reason I'm showing it to you here. V sub Ec is what we call the electrochemical potential of the species, with units of joules per mole. V sub C is the chemical potential, also in joules per mole, so the dimensions are correct, and of course V sub E is the electric potential in volts or joules per coulomb. Z sub I here is just the valence charge of the species. Just a number. For example, it would have been positive 2 for the zinc ions we were dealing with, or negative 2 for the sulfate ions. Its placement in the equation kind of makes some sense because you would only expect the electric potential to contribute if the species had a net charge, or Z sub I is non-zero. So the point of this equation is to show that the electrochemical potential is really just a linear combination of the chemical potential and the electric potential. Now we have to revise our definitions to say that two conductors connected together will allow charge to flow until the electrochemical potential is constant between the two. So electrons begin to flow because the copper plate is at a higher electrochemical potential than the zinc plate, because the copper plate is at a higher chemical potential than the zinc plate, even though they're both at the same electric potential. Why should electrons flow from the zinc to the copper though? Because both plates try to end up at the same electrochemical potential, so if we take away electrons from the zinc side, that whole side has less electrons, so it becomes more positively charged, meaning its electric potential gets higher, and from the equation we just looked at, if the electric potential on that side increases, the electrochemical potential on that side increases as well, roughly speaking, and it gets closer to the large electrochemical potential that the copper has. The copper side starts out at a higher electrochemical potential, so after that side receives negatively charged electrons, its electric potential becomes smaller, so its electrochemical potential gets smaller too, moving closer to the electrochemical potential of the other side. That's why electrons naturally flow from the zinc to the copper. Electron flow in that direction brings the electrochemical values closer together, while electron flow in the opposite direction would actually make the electrochemical values diverge from one another. But there's still one problem here. Why is it that when we just touch two pieces of metal together, nothing happens? Their electrochemical potentials are different, right? So wouldn't they want to exchange electrons? For that, we have to dig a little deeper into this aqueous solution chemistry stuff that's going on and ask ourselves, what's really going on each side? On the side with the zinc and zinc sulfate, there's a tendency for this chemical reaction to occur. We say the solid zinc on the plate is being oxidized to produce an extra aqueous zinc 2 plus ion in solution to join all the other zinc ions along with two electrons, and it's these electrons that have a propensity to travel down the conducting wire. On the other side, we have copper 2 plus ions in solution that now see these electrons show up and want to pair up and form a solid copper atom. We say the copper is being reduced. It started out as an ion with 2 plus, but that 2 plus has been reduced to a net charge of 0, and the ion from solution becomes a solid copper atom that clings on to the rest of the copper, leaving behind a net negative sulfate ion that can hang out with the rest of the gang. It's specifically these aqueous reactions that have a natural tendency to work out, reducing the mass of the zinc and increasing the mass of the copper. But when we just have solid copper touching solid zinc, there's no real spontaneous reaction going on here. What would we even say? These solid atoms are pretty stable where they are, and they don't want to end up producing ions, and there's also nowhere for any ions to go, so nothing happens. It's specifically these thermodynamically spontaneous reactions that occur when the two metals are in solution like this. So now that we know these half reactions have a tendency to create the same electrochemical potential on each side, we run into just a bit of a problem. As soon as the first two electrons leave this zinc plate, we have a new zinc 2 plus ion in solution, meaning the solution now has a net charge of plus 2. So the electrochemical potential on this side is more positive than it was before the electrons left, because the electric potential is more positive. As for the other side, we have copper 2 plus ions in solution that want to pair up with these electrons. So we've just lost a positive 2 ion in solution, giving this side a net negative 2 charge, and a lower electrochemical potential, because the electric potential is lower due to more negative charge. Then the electrochemical potential difference between the two sides is smaller as well, and it's going to keep getting smaller until the difference goes to 0. They're at the same electrochemical potential difference. But isn't that counter to what we've been saying all along with the potential difference across a battery being constant? Here, the potential difference across the two sides is decreasing over time. So what gives? We see the problem here is that on the zinc side, we're having a slow buildup of positive charge in the form of the zinc ions. And on the negative side, we have a slow buildup of negative charge in the form of the sulfate ions. One pseudo solution you could come up with is just use bigger beakers, and then it'll take longer for their electrochemical potentials to equal out, because there's more room for the ions. Kind of similar to how if you have a charged conducting sphere, if you increase the radius of the sphere, you can increase the charge on the sphere too, in order to get to the same original electric potential. But that's like putting a band-aid on a bullet wound. We haven't actually solved the problem of the potential difference getting weaker, we've just slowed it down a tiny bit. There's one last piece of this contraption that we've been saving until the end. You see, the fundamental problem with what we have here is this buildup of charge within each of the beakers. So what if every time 2 electrons left the zinc side and we have a new zinc 2 plus ion in solution, we just made it disappear? And every time the copper side had one of the positive ions come out of solution to join up with the 2 electrons, we had a negative sulfate ion just disappear to rebalance the charge. That would make things pretty convenient, wouldn't it? All of a sudden, our potential difference stays constant between both electrodes because there's no charge buildup. It turns out we can't exactly perform that level of magic, but we can get pretty close, and that's with this thing called the salt bridge that connects the two solutions. The salt bridge is just a tube containing aqueous solution of some salt that ionizes really easily, like sodium chloride for example, and it's got porous plugs on each end to prevent the solution from leaking out into the beakers, but still allowing ions to slowly transfer back and forth across it. Then this salt bridge acts as our solution to the very problem we were facing, because now when excess positive zinc ions end up in here, they don't like being near each other, so they try to find a way out, and this salt bridge allows them to escape. On the other side, when we have excess negative sulfate ions, they don't like being near each other either, so they can escape through the salt bridge too. And over time, these two collections of ions, they don't necessarily bond together, but at the very least they establish electrical neutrality between all of the solutions here. There's now roughly no net charge stored anywhere. And this right here is a working concept of a battery, known in chemistry as the galvanic or voltaic cell, named after Luigi Galvani and Alessandro Volta. There's an interesting story between the two of them involving the invention of the battery and a frog, which I encourage you to read about if you're interested. And yes, Alessandro Volta is the guy who we named the unit for electric potential, the volt, after. Taking advantage of the fact that electrons highly favor traveling through conducting wire, and aqueous ions highly favor existing in solution and traveling through it, we've created a device that maintains electrical neutrality between both sides, so the electrochemical potential difference between both sides remains constant, while spontaneous electrochemical reactions produce the flow of electrons from the zinc terminal to the copper terminal. Pretty ingenious if you think about it. There are a few things now that can cause this battery to stop working, or die, quote unquote. The most obvious one being, if we just use up all of the available zinc with electrons ready to give up on the left side, then there's no more zinc to go around and the battery's kaput. There are a few other complicated conditions that'll probably occur before that happens though, like in certain types of cells you can have solid waste accumulate too much, or in a cell like this, the concentrations of ions may eventually just become too large to thermodynamically favor the creation of more ions on either side. But we got a while before that happens. In any event, we got ourselves a working battery that can last a while. It's a pretty crappy battery though, and we'll see why in the next lesson from a physics perspective, and what we can do to make our battery more efficient.